Ever wondered how machines perceive the world around them, making sense of images and visual data? It's not magic, it's the power of convolutional neural networks, or CNNs. But today we delve deeper into a special kind of convolution, a method that has revolutionized machine learning, the separable convolution. Imagine an image, a vast array of pixel values. A convolutional operation, in essence, applies a filter or a kernel to this image, transforming it with the goal of detecting specific features. But traditional convolutions can be computationally expensive. Enter separable convolutions. So what is a separable convolution? It's a method that breaks down the convolution operation into two simpler parts. First, a depth-wise convolution, and then a point-wise convolution. Interesting, isn't it? So let's dissect each step to understand it better. The depth-wise convolution is the first step. Picture a single image with multiple color channels, red, green, and blue. Each of these color channels is a separate layer of the image. The depth-wise convolution applies a filter to each of these layers independently. This step helps in capturing spatial information, the where of things within the image. Next, we have the point-wise convolution. After the depth-wise operation, the layers of the image don't talk to each other. They're like islands, isolated and alone, but the features we're interested in might span across these layers. So we need a way to mix this information. That's where the point-wise convolution comes in. It's essentially a regular convolution with a twist. The kernel size is 1 by 1, hence the name pointwise. This step blends the independently filtered layers, capturing channel-wise information, the what of things within the image. In essence, separable convolution is a two-step process. The depth-wise convolution captures spatial information, and the point-wise convolution combines these spatial features across different channels. Together, they make up the separable convolution, a method that reduces computational cost while maintaining efficiency. To sum it up, separable convolutions offer a more efficient way to handle convolutions in CNNs. By breaking down the convolution into a depth-wise and a point-wise operation, it optimizes the computational process without compromising on the ability to detect features. Digital cameras can take photos at very high resolutions, but it's not just about seeing, it's about understanding, and separable convolutions help machines do just that.